Okay, welcome back, everybody. Hope that quiz was a little bit nicer than the exam. The exam was pretty rough. I've got graded it. I'll hand it back in a little bit once we finish the material here. Um, I'm going to make some adjustments. I realize now that it was a little too hard upon giving it. It was definitely longer than I anticipated, and yeah, just a little bit more difficult than I had initially uh, expected. That being said, so I will that's the great thing about the exam redo policy is that it allows me to uh, adjust for minor nuances here or there. So for this exam, instead of it being a 50% back, you're going to be able to get up to 75% back. So we'll talk about that more in just a little bit. So that will make things a lot better for a lot of students. So we'll get to it. We'll get to it in a second. But just suffice to say, let's say you got a 30, or sorry, let's even go with the 20. If you got a 20 on the exam, 75% of 80 points missing is 60 points. So you can go from a 20 to an 80. So that is a big possibility. So that'll help a lot of people out to adjust for the hard nature of the exam. That is probably going to be the hardest exam in well, no, that's a lie. Um, exam three will be by far the ch most challenging. Exam three has to do with all the convergence and divergence tests, which always ends up being a little bit daunting at first, but we will talk about it. We'll get there. We'll have some fun. Uh, but this exam, I don't foresee it being like this next exam. I don't foresee it being as challenging as the first exam. Okay. Any questions before we get started with the material for today? Okay. So, as a reminder from last time, the key thing about cylindrical shells method and how it works is it allows us to integrate ones that we wouldn't necessarily be able to integrate nicely if we had it with dy washers or dx washers instead decide to do dy shells or dx shells respectively. The main thing to keep in mind though is that you have to think about this geometrically when we're talking about these cylinders, the radii of these cylinders, they stem from the center of that cylinder. So in this previous example, this is the center of our cylinder. So the radius is stemming out from here. We are integrating from 0 to square root 3. So this is our x value for this random cylinder that we're drawing. I think we erased it. Um, And so when we try to figure out the radii, when we're rotating around different centers, we need to keep that in mind. And the key little hack or little trick that I told us last time is that the radii will, like 99 out of 100 times, be one of these three options. Either it's going to be your number, your center, plus x or y, depending on the situation, if you're rotating around the x or y axis, or your center number minus your variable, or your variable minus your center. It all depends. So if you're ever stumped and you don't know which one to do, just try it for different radii test points and you can see which one works best. And I'll show that again on this one to better understand it. So with this one, the whole thing was that this distance, I don't know why I wanted to add photos. Weird. But coincidentally, how did I get to that? How did I add photos? How did I do that? Did anybody see what I did? I have no clue. Well, regardless, we'll find out later. Um, so with this one, the center is at square root 3. This whole distance is square root 3. And so, since our radii stem from the center, and this right here is x, it'll be square root 3 minus x. So the volume formula using cylindrical shells is 2 pi r times your height. 2 pi times your radius times your height. And the height here, there's no bottom function. It's just the square root of x squared plus 1. So the formula for the volume would be the integral from 0 to square root 3 of 2 pi times your radius, which is square root 3 minus x, times the height, which is x squared plus 1 dx. And that is our, sure, we'll kind of move this down just a smidgen. There we go. And that is our formula. Any questions on that? Yes, Nick.
Sorry, how did it go that the purple segment is X?
So, excellent question. Excellent question. The fact of the matter is, X is always ranging from where you're integrating over, right? So, and we use our bottom bound as our starting point. So we start integrating right here. We start at 0 and go to square root 3. And so it's always going to be measuring like from the origin to that point. All right. All right. So the next one, we're rotating around x equals -3 instead of square root 3. So let's go ahead and just draw our picture again. So we have this shape. And then it was a blue line here. And that's square root 3. And this is y equals square root of x squared plus 1. And then our center, I'm going to put it right here. At negative center, x equals -3. And we're rotating about this line. So we get a mirror image. Wait a minute. Will it let me do it? Will it let me? Oh, that's a new feature. It allows me to mirror it. Oh my God. But the only thing is I need to make sure that I change the color because otherwise it's very confusing. Amazing. That's how you know you've made it to adulthood, when you're excited about that type of thing. Okay. So that's the picture we should get. And let's just pick a generic one for our arbitrary cylinder to try. So it's a DX shell. So as a reminder from last time, the variable that you use for a shell is it is opposite of the lines you're parallel to. So this is a line parallel to the y-axis, so we're going to be doing a dx shell. Okay, so how do we know what the radius is? Now, you can do it visually, and that's what we're going to do, but I'm going to show you how you can bypass it if you're truly stumped on an exam. We know it's going to be one of these three. We're either going to have, let's fix this actually. It should be the absolute value of A. I need to make that fix. That's what I thought. That's what I realized. It should be the absolute value of A. Please change it to the absolute value of A. In the little hacksaws section. Apologies about that. So it should be absolute value. So in particular, it'll either be 3 plus x, 3 minus x, or it'll be x minus 3. Because the absolute value of negative 3 is 3. Now, we want to know which one will be the right choice. So what we can do is we can pick a couple test values, test radii, to see whether or not it stands up. So if x equals 0, what should the radius be? Looking at this thing, knowing that this is negative 3. So when I am here, when I'm integrating my first cylindrical shell, when I'm forming my first cylindrical shell with an x value of 0, what's this distance? 3. So when x is equal to 0, r should equal 3. So don't write what we're writing over here. By the way, we're gonna make it more pretty, and we're gonna do the visualization later, but I want to show this. So with that in mind, well, 3 plus 0, that's 3. That is a potential candidate. If I do 3 minus 0, that also equals 3. So those two are possibilities. But if we do the purple one, we get 0 minus 3. That's negative 3. This one is out. So we've reduced it down to 2 choices. Now, if we don't know what to do from there, we got a 50-50 chance of getting it right. All right, so that's good news. But I'd rather be more precise than 50-50. And so what I'll do is I'll pick another one. Now you can pick the outermost one, which is usually a safe bet. That's usually a safe bet. But let's say you don't want to use that square root 3. Maybe that's kind of given us a little bit of a wonky situation. So we can pick another one. Let's pick x equals 2. No, not 2. That's greater than square root 3. 1. So right here at 1, what should this distance be? What should that radius be? 4, right? If x is equal to 1, the radius will get 1 more bigger. And so the radius should be equal to 4. So does 3 plus 1 equal 4? Yes, it does. That is a good candidate. Does 3 minus 1 equal, that equals 2? That's out. So we know it must be 3 plus x. So we've done it by trial and error. That is one way to do it, and that is especially useful if you are truly stumped and cannot figure it out. But now that we know that, now that we've seen that in action, let's go ahead and do it visually. So what we do know is that x is ranging from here to here. And this distance is 3. So our radius, which stems from our center, is there. So that'll equal, as we saw earlier, 3 plus x. So now that we have that, we have everything we need. We already know the height. There's no bottom function, so it's just going to be square root x squared plus 1. We know our radius, and we know the rest of the formula because the area of each cylinder would be 2 pi RH. We have R, we have H, we have everything we need to know for the volume. The volume will therefore be the integral from 0 to square root 3 of 2 pi R, which in this case is 3 plus x, times the square root of x squared plus 1 dx. Any questions on that? Good? Okay. Let's go on to the next one then. Set up the definite integrals needed to compute the volume of the solid generated by revolving the regions enclosed by 3 over x y equals 3 and 1/3 x about the following lines. So much like on the exam, I will make sure that there are ample scratch paper to sketch regions. So with this one, 3 over x, that has, let's zoom in and do that. So 3 over x, that has the point 1 comma 3, 3 comma 1, and it looks roughly like that. That's y equals 3 over x. Y equals 3, well, that's the line, that's the horizontal line going through the line, the y value 3. Y equals 3. And then 1/3 x, that's a line with slope 1/3 centered at the origin because it has a y-intercept of 0. So we go up 1 over 3 to find another point. And it looks roughly like that. Right there. Let's get a little bit better. Yep, there we go. Wait, no. That's not looking pretty enough. There. There we go. There we go. And that's y equals 1/3 x. Okay. So now it just so happened that when I drafted, I found the intersection points quite nicely. But let's go ahead and find them by hand. So the intersection points between the red and the blue, I just need to set 3 equal to 3 over x. And solve that equation. Looks a little familiar. Multiply both sides by x. Or you can kind of just guess it with this one. It's not too terrible to do, but I'm going to multiply both sides by x and get 3x is equal to 3, which gives me x equals 1. So here's 1. That's where the red and the blue curves intersect. Then we set the red equal to the green to find another intersection point. So 3 over x equals 1/3 x, which you could really write, by the way, as it's called. You could really write it as x over 3. And you could do cross multiplication, however you want to do it. I'm going to multiply by the LCD of everything. So I'm going to multiply both sides by 3x because that's the LCD of this thing. Doing so will give me 9 equals x squared, which gives me x equals plus or minus 3. However, one of those ones is not really necessary because this is just the right half of 3 over x. There's also the left half, which looks like that. That's where the other intersection point is. But you'll see that if you continue this region out, this area is unbounded, so that's not the region in question. So this is not the one we need. We'll ignore that one. So it's just x equals 3. And last but not least, we have to do the blue equals the green. So that's 3 equals 1/3 x. But that's a very, very quick calculation to say that x is equal to 9. Yes, Parker.
So all we're doing is for each of the equations, we set them equal to the other equations.
Yes, so that we can find where they all intersect. So in this case, there was a lot of intersection points. A lot of the times it's usually just two curves, and we just set them equal to each other. And we can find the 2 or 3 values where they all meet. But this time it's a little bit different. Any questions on that? So now we know all the x values and then and we can find the corresponding y values because we might need to do dy stuff. And if you plug in x, so for the place where the red and the blue intersect, you can set it, you can plug in x equals 1 into either equation. Well, you can't plug it into the blue equation, but if you plug it into the red equation, you will get 3, a y value of 3. And then here you'll get a y value of 1. Those are the two y values of the intersection points. Any questions on that? All right. So now we're going to rotate this region about the the y-axis. So what do we use? Red, blue, and green. Okay, so red looks like this. Blue is up top like that. And green is like that. And we're rotating it about this region. So cool. So you guys have to deal with it, but I just make it perfect now. Okay. So now that we know both methods, we can either do dx shells or we can do dy washers. Let's go ahead and label all the values here, by the way. This is 1, this is 3, this is 9, this is 1, and this is 3. Any questions on that? Now, my question to you, would dx shells or would dy washers be better? dy washers would be better. Absolutely. Think about y. Not the variable y, but why. The reason for that, Jose, is absolutely correct. And the reason is that if we do dx shells, we have to set up 2 different integrals. Now, in terms of just writing out the integrals, that's not too terrible. It's just a little extra writing. But if you're trying to compute the actual volume of this shape, that ends up being another integral to compute, and it's usually not as fun. So I'm going to recommend doing a dy washer. Want it to look better than that. And so it's going to be blue or green minus red. So let's go ahead and, so this is a dy washer. But one of the things that I would recommend to do sometime is to set up the volume with dx shells. And the cool thing is that now that we know both methods, if you can set it up, sometimes it's not possible, sometimes it's impossible to write one of the curves in terms of the other variable. But if you can set up the integrals and use your calculator to see if they're equal. If they are, you know you did it right. If they aren't, then maybe one of them is right and one of them is wrong, or maybe they're both wrong. Hard to say. So we'll go ahead and draw our little picture. We've got the outer radius is in green, the inner radius is in red. So R, capital R, the outer radius, is coming from y equals 1/3 x. And the inner radius is, little r, is coming from y equals 3 over x. But here's the problem. Do you see it? Isaac, what's the problem?
We have to convert, in terms of, that's,
Yes, we need to solve both these curves to be in terms of y. We need to get x equals stuff with y, which is not too terrible. I deliberately chose these functions to be not too terrible to work with. We need to get them in terms of y, so we'll write x is equal to 3y, and then this one is x is equal to 3 over y. So now that we have all of that information, we can set this up. The volume is equal to the integral. We're doing a dy washer, so our bounds and our functions should all be in terms of y's. So our bounds will be from 1 to 3. From y equals 1 to y equals 3 of pi times our outer, in parentheses, our outer radius squared, which was green, so it's going to be 3y squared, minus our inner radius squared, which is 3 over y, quantity squared, dy. Or if we want to make it look pretty, the integral from 1 to 3 of pi times 9y squared minus 9 over y squared, dy. I will accept either on an exam if I'm just asking you to set it up. So remember, my rule of thumb is that if you need to use your answer for something, the thing you found for something, simplify it. So if it was asking me to find the actual volume, I'd be using the bottom, the non-boxed answer, because that one is simplified-ish. Any questions on that?
just to go back to the word.
On the left side? Cool. And just to let you know, so I wasn't to be honest, I don't like my picture today. I don't like my picture. I think it's too thin. It's too hard to visualize. So this is a situation where if I had the time, I would definitely redraw it and maybe kind of over exaggerate the curve. Maybe I'd make it look like this. Just so that I can see it better. It's not a problem. We don't need to be perfect in our graphs, but sometimes it helps to redraw it. All right. Next one is about the x-axis. So I'm going to learn from my mistake here, and I'm going to make them a little bit larger this time. So the curve looks like this, then like that, and then like that. We are. And then because the future is awesome, mirror vertically. Oh, so cool. And that feature wasn't here like a week ago. So I'm just super jazzed about it. Okay. So we're rotating around the x-axis and we get this shape. So we could either do dx washers or we could do dy shells. And just like before, it makes more sense to do a dy shell than it does to do a dx washer. Because if we want to do washers, we'd have to split it into two pieces. We'd have to do this one, and we'd have to do this one. I'm going to stop doing the dashes, and I'm going to try and just see if I can. I'm an idiot. I'm an idiot, man. You know, for a person who's decently smart, I can be pretty dumb sometimes. So if we did do DX washers, which it wouldn't be too terrible, but that's what we'd have to do. I have a dashed line thing, but why not use it? So we could. I'm not going to. I'm going to do dy shells. So it's all right. A dy shell. And if so, then I need to know my y bounds. So 1 to 3. I'm not going to draw the 1, 3, and 9 on the x-axis because I don't need them. And so once again, the reason why we're doing a dy shell is this is just going to be consistently green minus red throughout the entire thing. Now, because we are integrating over the like we're rotating around the x-axis, the radius and the y value can coincide because it's nice and neat. So the radius of this thing is also equal to x, or sorry, to y. So r is equal to x, or blah, blah. God, r is equal to y. Because the radius and the y value that you're integrating over are coinciding in this case. So we have everything we need. We have the radius. The height of each of the cylinders will be green minus red. But remember, by a similar argument as before, this is the curve y equals x over 3. So we need to convert that to x equals 3y. And this is y equals 3 over x. So we need to convert that to x equals 3 over y. So the volume formula is therefore the integral from y equals 1 to y equals 3 of 2 pi times our radius, which coincides with y here, times the height of each of our cylinders, which will be green minus red. So it'll be 3y minus 3 over y dy. Any questions on that? And then to give you like actually what I'm going to do, and I'd like you to verify this on your own time. I'm going to give you the formula for the volume if you decided to use washers. That would be V is equal to the integral from 1 to 3 of pi times 9 minus 9 over x squared dx plus the integral from 3 to 9 of pi times 9 minus x squared over 9 dx. And let's see if I made a mistake while you guys are writing those things down. Let's see if they gave me the same number using my calculator. As a pro tip, when you're doing this, if you want to check your work, ignore the pi's because they're always going to have a pi in them regardless of it. And so just to make it look a little bit nicer, you can just ignore the pi's and then make sure that the same number, the number times the pi that you get. So let's see here, integral of 2x, it's 2y, but I don't have a y variable, 3x minus 3 over x, evaluated from 1 to 3. That is 40 pi, technically speaking. And then I will do the next one. I'll do, okay, so the integral of 9 minus 9 over x squared, evaluated from 1 to 3, plus the integral from 3 to 9 of, ignoring the pi's right now, I just factor that out front, so 9 minus x squared over 9. And I also get 40. So I got the same number. So I know I did it correctly. It's like if you don't get the same number, then either one of them is right or one of them is wrong, or both one of them is right and one of them is wrong, or both of them are wrong. But if you get the same number, 100% of the time you are correct with both setups. Any questions on that? Okay. Y equals 1. We're going to rotate around y equals 1. So let's go ahead and draw that center. Y equals 1 is right there. This is y equals 1. This is the center. And so this thing is going to touch the center right there. Sure. Doesn't need to be perfect. Actually, I'm going to start making it gray. That makes way more sense. Kind of a shaded version of it. Okay. So we're rotating about that purple line, or purple, I swear. I am a little bit tired, by the way. My son's birthday party went great. It was a lovely time, but I am exhausted from it. I'll show pictures during the break. But okay. From here, once again, I would argue that dy shells is the better option, in my opinion. That way I only have to do one. It's not wrong to do dx washers, but remember, since we're rotating around a different line, the radii change. And in fact, I think we should do both. I think we should both work through both of them. So I'm going to label these all. This is y equals 1/3 x, which, because we're going to be working with both of them, that's also equivalent to x equals 3y. And then this curve over here, that is y equals 3 over x, which is equivalent to x equals 3 over y, depending on the situation that we need. Love hearing all those pens click, clack. Excellent. We should probably take our break after this problem. Yeah, do that. Okay. So let's draw a generic cylinder for our dy cylinder. Okay. So this is our radius, because the radius stems from the center. Y is being integrated. It starts down here. This is y. And then this distance right here, this linear distance, is 1. So what is r? Take a second. Y minus 1. It's okay. Trust me. I really sucked at this at first myself. Truly. This is something I took a lot of time to try and figure out myself. So r is equal to y minus 1. But let's verify it. Let's use the if we ever get stumped, let's use the trick. So it's either going to be 1 plus y, 1 minus y, or y minus 1. We'll look at the very first cylinder, the dot cylinder right here. What's the radius of the cylinder at y equals 1? It's a non-existent, so it has a radius of 0. So if y is equal to 0, we should get r is equal to, if y is equal to 1, we should get r is equal to 0. 1 plus 1, that equals 2. That one's out. 1 minus 1, that's equal to 0. That's a potential option. 1 minus 1, that's equal to 0. That's a potential option. Now we just need to look at a different one. Let's look at the furthest out one. If y is equal to 3, if we're right here, what is the radius going to be? It's not 3. 2, because here's 1, here's 3, this is a distance of 2. So when y is equal to 3, the radius should be 2. So which one would that be? 1 minus 3, does that equals negative 2? That's out. So it must be this one. It must be y minus 1. And you can even verify it. 3 minus 1 is equal to 2. So that's why it's y equals, like the radius is y minus 1. Are there any questions on that? So you don't have to have the visualization memorized. It's especially useful if your cylinders start becoming a little bit too muddied up in all the visualizations. So now that we have our radius, we have our outer and inner functions. The heights have not changed of these rectangles because we didn't shift it left or right as well. So at the end of the day, then, our volume is going to equal the integral from y equals 1 to y equals 3 of 2 pi times our radius, which is y minus 1, times our heights of our cylinders, which is going to be green minus red, and it needs to be in terms of y because this is a dy integral. So green is 3y, red is 3 over y, so 3 over y, dy. Now, here's a fun little experiment question for you to visualize this, because this always screwed me up as well. Technically speaking, they're the same shape, right? Like the part B and part C. Shouldn't they have the same volume? Do they have the same volume is what I should ask. Will they have the same volume? What do you think? They won't. And the reason for that is imagine that the radius here, the radii here are going to be smaller. So when you make the whole thing, it ends up being a larger band. So the way I like to think about it is imagine if you have like a donut, right? If I have a donut and I just eat the outside like a monster, if I eat the outer half, so here's a cross section of the donut. If I just eat this area, I'm actually eating more donut because it's wider. It's a larger piece than the inside. It seems a little bit strange. At a cross section, it's the same amount. At a cross section, it's the same amount, but this thing is being wrapped around. So the outer piece has more area or has more volume. It's kind of a weird situation, but that was one of the problems on my homework assignment in Calc 2 was to calculate the area of the outer half of a donut with the generic formula for a torus, which was not too fun, but it was okay. Okay. Any questions on that? When I became a tutor for that class, they used the same homework assignments over and over again. I would just like when that problem came up, I said, just give it here. I'm not even going to explain. I'm just going to give you the answer. It was a bad time. I was not the best tutor in that situation, but you live and you learn. Okay, let's take our break. Let's come back at 11:15. All right, people watching the recording, do some push-ups or some sit-ups. I don't know. All right, so we're back. Good times. That is the way to work it for dy shells. I'd like you to try and figure out later today, try and do dx washers. Try and figure out dx washers, and I'll have the answer up when we come back on Thursday. Okay. One where it says find the volume. So this time we're actually going to have to compute it. Find the volume of the solid formed by rotating the region bounded by the curves y equals e to the x, y equals 5, and the y-axis about the line x equals -1. All right. So this is my first sketch. I'm going to do this on some scratch paper, but since this is the only scratch paper I've got, e to the x looks like this. Y equals 5 is like that, and the y-axis is that. So it looks like this. So now that we've got that under control, let's go ahead and draw it prettier, and then also find out the intersection points. So we're working with this region. That's y equals e to the x. That's y equals 5. And we're rotating this about the line x equals -1. So this line here. This is the center. X equals -1. Nope. Style, will make it gray. Okay. Okay. So, dy washers would not be the worst idea in the world. But because I remember I wanted to do something very particular with this example, we're doing dx shells. Deal with it. But you could definitely, well, you know what? It would also do the same concept. So I wanted this one to require us to use integration techniques to figure it out. And if you use the other one, if you decide to do dy washers, it will still require you to use integration by parts. But let's just do a dy or dx shell. So let's pick a random one right here. And we'll that's our dx shell. So this is a distance of 1. X is being, oh, we need to find the intersection points. Silly me. Let's go find that out. This is one thing I do love about this area of mathematics is that there is no one right way to do these problems. You'll realize halfway through that you forgot something, like I did just now. And so we need to set the purple equal to the blue. So we've got e to the x equals 5, which means that x is equal to the natural log of 5. The way we did that, by the way we calculated that is we applied the natural log to both sides of the equation, canceling the e with the ln. Does anybody need to see that, or are we all good? It's okay if you do. You want to see it? Yes, absolutely. So the one middle step, thank you for asking. So The way I typically write it is I say apply ln. So natural log of the left equals natural log of the right. So that is to say natural log of e to the x is equal to natural log of 5. And the whole point is the ln and the e will cancel each other out because they are inverse operations, like a square root and a square, or a cube root and a cube, or a 1/2 and a 2. So this is square root, or this is natural log of 5. And we know that this distance right here, this is a distance of x. And then the radius stems from the center. That's the radius. So the radius should be 1 plus x in this case. But as before, you can always use your different things to try and figure out what would be best. All right. So we have everything we need. Go ahead and set up the integral now that we have that, unless there's any questions. Okay. So I'm going to write it. The volume should be the integral. The bounds are from 0 to natural log of 5 of 2 pi times our radius, which is 1 plus x, times the height, which will be 5 minus e to the x dx. Okay, and then we have to find the volume this time. And while it doesn't look exactly fun, I mean, it does seem like a little bit of fun, right? It's a little bit of foiling, a little bit of fun. But if it looks a little intimidating in all these multiplications, let's FOIL it out like normal. And honestly, leave the 2 pi to the end. Don't worry about it. Like, you're just gonna have to keep rewriting it. So why not just leave it till the end? So this is equal to 2 pi times the integral from 0 to natural log of 5 of 5 minus e to the x plus 5x minus x e to the x dx. Okay. 5 minus e to the x plus 5x minus x e to the x. Okay. Just by foiling it out. Now, 3 of those pieces are very, very quick. The integral of 5 is going to be 5x. The integral of e to the x is going to be minus e to the x. And the integral of plus 5x squared is going to be plus 5/2 x squared. Sorry, 5x will be 5/2 x squared. Those ones, not too terrible. But this last one is going to be something that's going to require a little more nuance. So let's compute that off on the side. The integral of x e to the x dx. I'm going to make sure I remember the minus sign. So as a little pro tip from myself, highlight it. Bring a highlighter or a colored pen with you to remind yourself. I just don't want to deal with the minus sign while I'm working on this little integral. I'll add the minus sign at the end. But that's me. That's my personal opinion. You can choose to do it your way if you'd like. All right. So what integration technique should we use? Integration by parts. It doesn't involve trigonometric functions, so it's not a trig integral. It doesn't involve rational functions, so it's not a partial fraction decomposition. It doesn't involve square roots or anything of the form x squared minus a squared or x squared plus a squared or anything like that. So it's not a trig sub. Only other option we have is integration by parts, which is correct. U is equal to, so following LIPET, logs, inverse trig, polynomials, then exponentials. X is a polynomial, so we'll make u equal to x, so that du is equal to dx, and that means that dv is equal to e dx, So v is equal to e to the x. Because the antiderivative of e to the x, so dv is equal to e to the x, the antiderivative of that would just be itself. So it's going to be uv minus v du. So x e to the x minus the integral of v du, which is just e to the x dx. So at the end of the day, then, this is equal to x e to the x minus e to the x plus c, but we're not doing that. We're doing a definite integral. Any questions on that? So it's going to be minus parentheses x e to the x minus e to the x. Any questions on that? Now that we've got everything set up, let's go ahead and bring it all down. Now that we've, like, in the red, blue, green, and purple, we found all the antiderivatives. Now that we've found those, we can use the fundamental theorem of calculus to actually compute it. So it's going to be 2 pi parentheses 5x minus e to the x plus 5 halves x squared minus x e to the x minus plus e to the x, evaluated from 0 to ln of 5. Tedious, yes, but nothing too terrible. Keep in mind, by the way, that e to the ln of 5 is 5, and e to the 0 is 1. So this will equal 2 pi times brackets parentheses 5 ln 5 minus 5 plus 5 halves natural log of 5 quantity squared minus 5 natural log of 5 plus 5. That's the first part. That's evaluating a natural log of 5. 5 ln 5. Really? Oh, well, oh. The e to the x is canceled. Interesting. We don't even really need to write it. Whatever, we'll still write it. Just want to make sure I've like, that's a lot of terms, and so I'm just making sure right now. 5 ln 5 minus 5. 5 halves natural log 5 squared minus natural log 5 times e to the natural log 5, which is 5. So 5 ln 5 plus e to the ln 5, which is 5. Good. All right. Any questions on that? It's okay if there are. Minus in parentheses, well, 0, 5 times 0 is 0, minus 1, because e to the 0 is 1, plus 0, minus 0, plus 1. Okay, well, let's do some canceling out. Though that being said, on exam, I feel like this will be fine. But let's go ahead and do it. So the 5 ln 5s cancel. The 5s cancel. The 1s cancel. And so this is just equal to 2 pi times 5 halves times natural log of 5 quantity squared, which is just 5 pi natural log of 5 quantity squared. Technically units cubed, but whatever. Yes.
Question. For the other ex, it just turns into 5, but how come for the xe to the x?
It's 5 ln 5?
Yeah.
Excellent question. So when I plug in natural log of 5 into this, what it ends up being is natural log of 5 for the x times e to the natural log of 5. But then the e and the ln cancel. Good? Excellent question. Yes. All right. There we go. That makes sense to me. Yeah. I agree. All right. It's time to go. Any questions on that? Okay. That was all of those ones. One thing I realized that we never got around to doing is one of the questions in 2.1 on the area between curves that was super awesome that we didn't get to do, which was this one. So if you'd like to go back and you notice this one, consider the region in the first quadrant bounded by the curves y equals m squared x and y equals x cubed, where m is some positive constant. We don't know what it is. For what values of m will the area of the region in question be equal to 64 units squared? Okay, little intense at first, but I promise you there's when you see these types of problems, if you have a weird variable square, like an unknown value squared, like m, it's probably deliberate that I'm choosing it to be m squared because that'll make it nicer to work with, as you'll see in a second. So this time we're dealing with area, not volume. So x cubed, we're drawing a rough sketch to start it off. So this is x cubed, right? So y equals x cubed. And y equals m squared x. M is just a constant. So y equals mx squared. So note, y equals m squared x is a line with slope m squared and y-intercept equal to 0. So what that curve looks like is like this. That's y equal, and this is my rough sketch. Once again, this is not something I'm drawing perfectly right now. I'm going to make it better in a second. But it looks like it has a piece down here that's intersected, but we want only the piece in the first quadrant. So we want this little slice that I've got. So now that we've done that, now we've drawn a rough sketch, let's draw it prettier and find out the intersection points. So it's going to be like this. That's y equals x cubed. And then like that. And that's going to be y equals m squared x. So this is 0. And this is going to be some value. Let's find out what it is. The int point. We're going to set the two functions equal to each other like normal. So x cubed is equal to m squared x. And that's a polynomial equation. So we'll bring everything to one side. X cubed minus m squared x is equal to 0. Factor out a common factor of x. And that's why I had m squared. That's why I had m squared. Because otherwise I'd have to deal with the square root of m, and I don't want to deal with that. That's not fun. If I just made it y equals mx, that wouldn't be as nearly as nice. But that fact, so that gives me x equals 0, m, and negative m. So this is m right here. Any questions so far? Good. All right, now we know the bounds, we know the top and the bottom functions, we can compute the area. The area is equal to the integral from 0 to m of the top function, m squared x, minus the bottom function, which is x cubed dx. And it says in the problem, we want to find the value or values of m that will make the area of this region equal to 64. So we want to set this equal to 64. Now we're ready to go. Yes, m is a variable, but it's a fixed variable. We just need to find out what it is. And guessing is not sufficient. We have to figure it out by hand. Or with a calculator, you know, like with ChatGPT, that type of thing. It's getting a lot better at math. It's pretty crazy, actually. But either way, m squared is a constant. So this is going to be m squared over 2x squared minus 1/4 x to the fourth, evaluated from 0 to m. The antiderivative of x is x squared over 2, so that's why it's m squared over 2x squared. And the antiderivative of x cubed is x 1/4 x to the fourth. Plugging that into our like doing the fundamental theorem of calculus, that gives me m to the fourth over 2 minus m to the fourth over 4 minus 0 minus 0, which is m to the fourth over 4 at the end of the day. Factor out the m to the fourth, and you've got 1/2 minus 1/4, which is 1/4. And that equals 64. So that gives me m to the fourth equals, what is 64 times 4 is 256? Nice. 256. To solve for this, we will take the fourth root of both sides. But when you do that, remember you have to have the plus or minus. So m is equal to plus or minus the fourth root of that. Raise that to the 1/4 power. It's 4. Now, because it's squared, m could be either +4 or -4, and it just ends up being the same thing. But actually, the only run that really works is m equals +4 to make sense in this context. Wasn't that a cool problem, though? It's cute. It's a cute problem. All right. I'll be sending out the Unit 2.4 notes probably tomorrow, later in the day. Still kind of getting some last minute things put onto it. But be prepared for that. I'm going to go ahead and pause the recording and pass back the exams. Okay, so I just handed them back. One thing I want to say as a reminder about things: one score does not decide who you are as a person, nor does it decide who you are as a mathematician or a student. I have, to be completely transparent, I actually failed my several of my exams. I have. I got a D in math 285. 285 part 2. I got a D in that class. I still got into grad school. I don't teach differential equations just because I hate it. But either way, I can teach it. I just don't want to. Keep in mind also that score is not actually reflective of what your true score on the exam actually is. As I said earlier in the hour, I'm going to be giving up to 75% of the points back. So this is how you can figure out your score. Redo score, which so people who've had me for Math 181 or before, you know that the original score is not actually your score. The redo score is your true score on my exams. So it says redo score, but it's actually the true score of the exam. It's going to equal the original score plus 0.75 times 100 minus the OG score. So that's 75% of the points you missed. 100 minus your original score would be the amount that you missed. So as an example, if you get a 20, it'd be 20 plus 0.75 times 80, which ends up being an 80. So you can jump up quite a significant portion. So I feel like that is far more indicative of your actual understanding of the course, not a 20%. That's why I'm adding, I'm adjusting the grade that way. This was purely a me situation, not a you guys situation. I made this exam too hard in retrospect. You are allowed to do the extra credit problem as well. Not to put your score above 100. Not to put your score above 100. So if you haven't done it and you get like a 96 or whatever, and you do the extra credit problem and you get a 5 out of 5, I'm going to cap it at 100. So you can get no getting over 100, but you can get up to a 100 in certain circumstances. Okay. How it works as a reminder. is that you have to do, you can redo any of the problems that you missed. You don't have to redo all of them. And you don't have to redo the ones that you didn't do. If you don't know how to do one of them, then just leave it blank. I will still grade the rest of the ones that you did for the redo. So it's not, you don't have to do the whole thing over again. It is not on a time limit. It's done like a homework assignment. You do it at your own pace. And we'll talk about the due date in just a moment. But it is going to be, that's how it's going to work. So you can take it home, work on it whenever. You can turn it in as soon as you want. You can turn it in before the due date if you'd like. And then please also remember that you should write a little blurb. It doesn't need to be a lot, but just something to say where your mistake was. Like, I tried to use trigonometric integration when it was supposed to be trigonometric substitution. Or I tried to use partial fraction decomposition with a square root, which doesn't work, and things like that. Or I forgot to complete the square first, or some, or I forgot to, on certain ones, like there's one where it was, you needed to do a over y plus b over y squared plus cy plus d over y squared plus 4. I forgot to do the a over y term. That happened to a couple people. It happens to all of us. Happened to me when I started. So it's not a problem. What else? So just make sure you write a little tiny blurb. It doesn't need to be an essay. Just like 1, 2, 3 sentences is fine. Any questions on that? What else do I want to say? Oh, that's right. Due date. So normally I would say it would be due in a week, but that would mean that you're spending precious time this weekend not studying for the upcoming exam, which I prefer if that was not the case. So what I'm going to actually do is I'm going to extend it till the Tuesday after the exam. So the exam is next Thursday on the 5th of March. The redo will be due on the 10th, which is Tuesday the 10th of March, okay? Any questions on that? As a reminder, should be you figuring these problems out by yourself with any resource that does not have a solving component. You can look up videos, you can look back over your notes, you can look up at textbooks, you can look at websites, you can look at other people's notes, like other teachers' notes and things like that. If you've taken it before, or if you find a teacher that you really like from a different school that has notes on it, you can use those. But it should be you looking at some resource to help you understand how to figure it out. The only exception is me. You can always email me with questions or come to my office hours with questions on the exam. And I'm happy to point you in the right direction. Even if it's a situation where you say, I just don't even know where to get started, I can definitely point you in the right direction. What I will tell you is that there's almost always going to be one question, at least one question in our notes that will help you understand how to do that problem. So you can you shouldn't need any outside resources. It should all be there in our notes. But if you want to, feel free to look at other resources. Maybe they explain it better than I do, or better for you. All right. Any questions? No questions. Excellent, guys. So once again, due on the 10th of March. So in 2 weeks, 2 Tuesdays from now. Okay, guys? I'll see you guys on Thursday. If you have any questions, feel free to email me. Oh, and then last thing, I'm sorry, I forgot to mention, please make sure that everything adds up correctly on the exam. And if you feel like anything was graded unfairly, please talk to me. I am not perfect. Sometimes I grade too harshly. Sometimes I grade not harsh enough. If it's the latter, don't let me know. If I graded it too nicely, don't let me know. If I accidentally gave you too many points, don't let me know. All right. Otherwise, have a great rest of your day. I'll see you guys on Thursday.